Here's our first example of hypothesis testing for population means. Sometimes, for short, this is called doing a t-test. In this first example, we're looking at some data that's collected about salaries, and you see that we've randomly selected 10 salaries to get an idea for what's happening in the population among all nurses. And if we look at the question, the statement of the question carefully, you'll see that there's a claim that the average starting salary is $24,000, and there is someone who thinks that the true mean is lower than that figure. So those are the hypotheses that we're looking for when we set up our problem. The mean that we're testing here is the average starting salary among all nurses. So like before, this should be a population parameter, but before we were looking at population proportions, here we're looking at a population mean. So don't forget the word mean is just another word for this, for the word average. Like with our proportion, our hypothesis testing for proportions, the null hypothesis is going to be a statement of equivalence about the population parameter that we're testing. So in this case, we're testing the population mean, mu, and the equal statement that we're testing would be mu is equal to 24,000. The alternative hypothesis in this case is what is given in the problem. In this case, it says that the researcher thinks that the true mean is lower than that figure. So mu is the true mean, lower than will be less than, and that figure is referring to the 24,000. So this is going to be a one-tailed test, to use the same language that we used when we were talking about hypothesis testing for proportions. Notice that if there was no statement like that about the researcher or person who's doing the test suspecting something about being less than or greater than, then our default decision is always to say not equal to and use a two-tailed test for our alternative hypothesis. So nothing in this is different, it's just that we have means instead of proportions. We have seen when we're building our confidence intervals that when we're looking at the sampling distribution for X bars, for sample means, the standard error formula, the distance between the tick marks, is given by a different formula than it is for proportions, which makes sense because there are no proportions in this problem. So the standard error formula it's the standard deviation over the square root of the sample size. So, so this would be the exact statement of what that means, but, and in fact I'll write equals here. But the fact is that we usually don't know what sigma is, and so we're always going to be approximating this using the sample standard deviation S divided by the square root of the sample size. So in this problem, we know that the sample standard deviation is 2273.37, so that's coming from here. And the only way I would know that, notice I did point out here how I got that. I used some technology. I put the 10 numbers into one of our web apps, and it gave me the summary statistics. One of which was the sample standard deviation. The N here is 10. There are 10 nurses, so we have the sample standard deviation 2273.37 over the square root of 10. And that is, let me look at my computer. On the output from my computer, it says that that's 718.90. And so now we can draw a picture of what we think the X-bar distribution, the distribution of sample means, will look like if we're sampling random groups of 10 nurses at a time and getting their average salaries. And like before, this picture we're going to draw is the picture based on the null hypothesis being true. So remember, the null hypothesis said that mu was equal to 24,000, and so if the null hypothesis is true, then 24,000 is going to be that center value. The standard error, like before, is the distance between our tick marks on this X-bar distribution. So if I were just to, let me just use 700 for that on my tick marks just to make it easier to write. So that would be 24,700. That would be 25,400. This way would be 23,300, and so on. So here I'd have 22,600. So if I just use the number 700 for my tick marks, just to be able to label them easily, that's about where they are. So now we're ready to actually use the data that we've collected and see how consistent the data we collected is with this hypothetical picture. So this picture is hypothetical, assuming H0 is true. So the actual sample mean, the X bar that we really collected, was 22,792.50. Again, that comes from computer output from me putting those 10 numbers into the web app that is linked up there. On the picture, I know that 22,792 is somewhere in this vicinity. So I can make a note of where it is up there. That gives me a visual sense immediately of whether this value seems all that unusual or not. The test statistic that we use is called the t-score, and it's actually exactly the same calculation as the z-score. We're just, we call it something different to remind ourselves that this X-bar distribution, even though it looks nice and symmetric and mound shape, really is not the same as a normal distribution, especially when the sample size is small. So to remind ourselves that that's really a different interpretation, we call it something different, but the formula is the same. So the formula, remember, was that it's our observed value, so that's this X bar value, minus the mean. And again, I'm looking at that picture. The mean on that picture is 24,000, that's right in the middle, divided by the standard deviation of that picture. In other words, divided by the distance between the tick marks. And I'll use my more exact value here. I don't want to use that drastically rounded off value. And I can actually do that calculation. My computer output says that's negative 1.68. So somewhere between 1 and 2 tick marks to the left of the middle, that is exactly what we saw where we sketched it out here. So that negative 1.68, remember, that will be telling us how many tick marks it is from the center. And so it's more than one tick mark from the center and a little bit more than halfway to the next one. So that is corroborated by that, that number is corroborated by that picture. All right, and then finally we get to the point where we really are going to rely entirely on technology. Well, I guess I'll draw the picture first. On my t-distribution picture, I would just draw my negative 1.68 as my t-score on here, thinking of the center is 0 and every tick mark is 1. So negative 1.68 would be right there. Because of the structure of my alternative hypothesis, notice it has a less than sign in it, and we always think about the direction of the shading is going to follow that like an arrowhead. So the less than sign would mean that I'm shading to the left. So I would shade in this area. Because it's a one-tailed test, it's not a not equal to sign up there, it's a less than sign. That's the only part that I'll shade. So the area of this picture is the p-value. So the area that I shaded right there is the p-value. When we were doing the other problems with normal distributions and z-scores, we could then just go to a table and look up the z-score of negative 1.68 and figure out how much area that has. The t-distributions are a little different. You get a different t-distribution depending on your sample size. So for every, what we call degree of freedom, there's a different t-distribution. So there's really no good way to do this by looking at one chart. And so that's why we just use technology to do the calculation for us. So from the technology, and the link is given there beneath where I'm writing. We can put the information in, including our hypotheses and our data, and it will draw this picture for us, so we can be sure that its drawing matches our drawing, so we know we have everything set up correctly, and it'll tell me that my area is 0.0637. So a little bit more than 6% of the picture is shaded in number 6 here. So remember, p-value has the same interpretation that it did before. P-value is the probability that you would get a sample that's as far away as you did under the assumption that the null hypothesis is true. So in other words, we can use that as a measurement of how compatible, how consistent the picture in number 4 is with the data that I collected. So in other words, we're measuring the compatibility of the null hypothesis being true with the data that we collected. So we have about a 6% chance that we would have data as far away as we do from the middle if the null hypothesis is true. So the problem, the original problem said that we're testing at the 5% level, and so this p-value is bigger than 5%. So I'll say since the p-value is not small, and again, the definition of being small can change from problem to problem, it's what we call the significance level. So in this problem, the significance level is 5%, which means that I'm going to think of probabilities of less than 5% as being small. So this p-value is not small by that measurement, so we do not reject the picture. We do not reject H0. And in fact, let me write that do not, so we can emphasize, since the p-value is not small, we do not reject H0. The other possible alternative there, the other possible statement we could have made would just be, since the p-value is small, we do reject H0. Those are the only two conclusions that we'll make. So in the context of the problem, we would say we do not have enough evidence to support, and then I always do my best to just say in words as well as I can the statement HA. So not rejecting H0 means not supporting HA. Usually, if I'm doing it, I'll go back to my original question and just make sure the HA in the original question was that the researcher thinks the true mean is lower than 24,000. So that's the alternative hypothesis in English. So we do not have enough evidence to support the claim that starting salary is less than 24,000. So that does not mean we're saying that the starting salary is something else. We're just saying that we don't have enough evidence to support that claim. Just so you know, in this PDF file that's posted that I just worked through, there is a second page. Actually, there's 2 more pages. On the second page is some screenshots of the numbers I put into the software to get the 2 steps in that process that I said we were going to use the computer for. So you want to make sure you understand how the decisions I made in setting this up. One thing that's not obvious is don't forget that when you're entering numbers, they have to be numbers. So in the original problem, the numbers had commas in them, there were dollar signs involved. You have to take all that stuff out to just have numbers only. So this is what the two web apps that I referenced would look like if you set them up for this problem. And then finally, I also included a page that has written answers to the problem so that you don't have to rely on sketchy notes if you want to just look at all the steps that we just went through to solve the hypothesis testing problem.